Alright, so today we're going to be talking about chemical equations and stoichiometry. So, first off, chemical equations, um, they represent chemical change. So, represent chemical change. And then stoichiometry, which we briefly went over, is a numerical relationship of the reaction. So this means mainly in moles, but you can do it in other stuff too. Anyways, so when we're talking a chemical reaction, we have reactants, then we have our little reaction arrow, and we have our products. So I'm going to do an equation dealing with water. So if I put 2H2 plus O2, I was wrong with my pen today, then we have our reaction arrow underneath. And then we have 2H2O. Now if you look at your reactants right here, if you look at those versus your product, you can clearly see you have the same elements, but they're different in that they have changed the way, well, they've changed their chemical properties, because now instead of it being hydrogen and oxygen, they're both in one molecule as water. So that's the whole idea behind a chemical reaction. Now, when you're writing down a chemical formula, I know I've gone over this before, but I'm going to review it. So you have coefficients. So say we have 2 and then H2. Actually, I'm going to do 2H2O because it'll make more sense. And then we're going to have another thing called a subscript. I'm going to use the same molecule to explain this. So looking at the coefficient would be right there. So the coefficient is kind of like in algebra when you have like a 2 and then you have your parentheses. You could think of this whole thing as a molecule. I'm going to go like this. So if I wrote 2H2O, you're going to go 2H2, 2O. So you're actually going to have 4 hydrogen molecules and 2 oxygen molecules. So the subscript is right here. That refers to individual elements. So if you had this, it's really only dealing with the hydrogen. So that means before you do anything with the coefficient, you have 2 hydrogens. You have 2 hydrogens, and then you have your coefficient. So all these things work together, and then I'm going to write the definitions down. So coefficient is just in front, and whole molecule. Then we have our subscript, and it's behind an element, and only affects that element. Now, if you need to copy this down, just pause the video. So when we're talking about chemical reactions, there's a very important natural law that comes into effect. So we have the law of conservation of mass. Now remember, I asked a few of you in class if you even ever heard of that, and you'd heard of it, you just didn't remember what it was. So the law of conservation of mass in a closed system which would be our universe. So write that in red. In a closed system, and then this is the important part, we have matter cannot be created or destroyed. It can only change form. Now I'll give you a second to look at that, and I'm going to draw a picture to show you what I mean. So, say I had the reaction 2H2 plus O2, and then we have 2H2O. Now, so here's our reactants right here. And then we have our reaction arrow. These are going to bond together, and then you're left with this. Now, if I go through, those are blue, these are red. I'm going to erase that. So if I count these, I have 1, 2, 1, 2. I haven't lost anything, and I haven't made anything extra. Now, if I count these, I have 1, 2, 3, 4. I have 1, 2, 3, 4. That's the whole idea behind stoichiometry, is you have to be able to balance your chemical reactions. We're not going to be creating things out of thin air, and we're not going to be losing stuff and not being able to explain where it went. So, that moves on to balancing chemical reactions. So I'm going to start off with an easy one. So we have Al, O2, and then we have Al2, O3. If you don't know how to get these balanced, I really suggest you review that. But usually I'm going to give you the molecules on a quiz or a test. So anyways, first off, we have to count how many elements we have on both sides. So what I always do is I draw a little line down the middle. And then on both sides, I write down the elements that I have. So I'm going to start on the right side. I'll do the right side in blue. So on the right side, I have 2 aluminums, and I have 3 oxygens. And then on the left side, I have 2 oxygens, 1 aluminum. Because I have 1 aluminum on the left side, the way I'm going to figure this out is I'm going to solve for the oxygen, because I can just multiply the aluminum over here by whatever coefficient to manipulate the equation and get it balanced. So the whole idea behind balancing is these numbers and these numbers have to be exactly the same. And that would be the law of conservation of mass. Now, since we have 2 and 3, I'm going to look at the oxygen. So if you looked at LCM, you have 2 and 3, that would be 6. So to get this to 6, I have to multiply the whole molecule by 2. So one thing I do when I do this, I cross everything off, and then I rewrite what I have. So this is where the coefficients and how to use them comes in. So I have multiply this one, multiply this one. You're multiplying this, not just by the letters. So that means that oxygen is going to have 6. Aluminum, let me do that in a different color. I'll do it in green. So oxygen is going to have 6. Aluminum is going to have 4. Now over here, I have to multiply this by something to get it to 6. Super simple. 6 divided by 2 equals 3. There you go. So you put the 3 in there. So that's going to change this to 6. And all I have to do is balance. Let me do it in green, because otherwise I'll lose you. See, all I have to do is balance this aluminum with this one, and that's easy because it's 1, so you just multiply it by 4. And now all of the numbers down here are exactly the same. You have a balanced chemical reaction. I'm going to write down, I'm going to do another example. This one kind of tricked a lot of people. It even tricked me up for a second because I wasn't paying attention to what I was doing. But I'm going to explain how to do it. So, let's say we have H2SO4. And this is another thing I told you guys to remember, your polyatomic ions. A lot of you have no idea what I was talking about when I said that, so I suggest you review the list I posted online, because it's going to make your life way easier. Okay, so once again, polyatomic ion, you have sulfate. That is one thing. So we're just going to write, I'm going to start off with that. SO4 is one thing. We're not splitting that up. If you split it up, one of my classes asked me to do it, and it took way longer to balance this. All right, so we have H, SO4, and A, and we have to still account for this oxygen right there. Same thing over here. We have to account for this one, because SO4 is its own thing. It looks like this. Let me go down here. This thing is not splitting up, but it has a charge due to these two oxygens right there. That's where it's a polyatomic ion. It's a charged molecule. All right, so we have H and A and O. So first thing I'm going to do is count everything I have. I have 1, 2, because I have 2 there. I have 2 here, and I have 1. Over here I have 1, 3, because I have 1 here, 2 there. I have 1, and I have 1. So, looking at this, I always like to start on the right side because that's what I'm going to have. You could start either way. It doesn't really matter. I'm looking at the molecules that are different. I have hydrogen, and I have sodium. Because hydrogen is on this molecule, it makes sense to start balancing with the sodium. So I'm looking at this, I have 2. To get 2 over here, I simply write a 2 there. Now I have to multiply everything by 2. So I have 2, and then now I have 2 of these. And I have 1, 2, 3, I have 4 of these. But I still have 1 sulfur. So right now I'm doing alright. But these, right now, are exactly the same. So I'm going to look over here. To get O to 2, because this one's 2, and then get H to 4, all I have to do is write a 2 there. So I write a 2 here, and that's going to make hydrogen 4. Sodium is going to stay the same, and oxygen is going to be 2. Now if you look at all these numbers, they're all the same. So all we have to do now, sorry, I forgot that one, is write in the rest. And that would be a balanced equation. It's not super difficult to do this. Sometimes they're a little tricky, but all you gotta do is remember to not split things up and kind of, attack it from a logical angle. So now I'm gonna go over why is this important. Why is stoichiometry important? So if I had 2H2 plus 1O2, these are my little things, and then I get 2H2O, that means that 2 moles, because remember the coefficients are moles, 2 moles of H2 plus 1 mole of O2 gives me 2 moles of water. So if you split that up, you have 2 mole H2 equals 1 mole H2O, or 2 moles, And then you have 1 mole of oxygen is 2 moles H2O. So it's really important to understand these relationships because this is how we find our limiting reagents and a few other things that are really important. Like maybe we could find how many grams of something we can make if we only have a certain amount of stuff. And that also deals with your limiting reagent. So I'm going to write down some rules on the next page because I think I'm out of room. Yeah. So let's go to here. We can use a balanced equation to determine the following. So, 1, amount of reactant needed to form a certain amount of product. 2, amount of product that can be formed from certain amounts of reactant. And lastly, amount of reactant needed to react with certain amounts of another reactant. Okay, so I know that was a little wordy definition, but the whole point of stoichiometry is to be able to pretty much calculate the amount of something you're going to make with the amount of something that you have by using a balanced chemical reaction as a guide. So, and then let's put that in there. Amounts equals grams or moles, depending on what you're trying to figure out. So I'm going to show you how to do this real quickly. And then, yeah, that'll be like it for this video. And then we'll do another video on limiting reactant or limiting reagent. So say I had 4H2 plus 2O2 is equal to 4H2O. This is just an example. How many moles of H2 are required to make 4 moles of H2O? So, how would we figure that out? Easy. You have 4 moles H2, and then we just type in or write in our thing. So you have so what this is saying is if you did 4 times 4 divided by 4, you're going to get 4 moles. If I flipped it around and said, how many moles of O2 are needed, I would just do oops, I wrote that wrong. My bad. Let me rewrite that. It's really sloppy. It's going to give the same answer, but I wrote it backwards. So these would cancel out, and you're left with 4 moles H2, because that's what we were trying to figure out. Anyways, 4 moles of H2O times 2 moles O2, and then we have 4 moles, because that's our ratio is 2 to 4, so it's technically you could simplify this even more, 1 to 2, and then you would get 2 moles H2O, or O2, because this cancels. So that would be an example of how to do this. And then, yeah, that's what we're going to stop today, and then I will go over this in depth on Monday.